Hello everyone. Welcome to my poster presentation. I am Fatemeh Ostadhossein, and I'm looking for a faculty position this year. I'm an NIH postdoctoral fellow at Stanford University working with Professor Joe Wu and Professor Sarah Halstern. I did my PhD at University of Illinois Urbana-Champaign under the supervision of Professor Dipanjan Pan. I was briefly a Beckman postdoctoral fellow there. In this talk, I will summarize my past, current, and future research. My PhD work was focused on developing drug-free theranostics, that is, therapeutic and diagnostic nanoparticles for localized and systemic diseases. My postdoctoral work investigates the role of soft materials such as hydrogels and nanoparticles for the delivery of a proprietary stem cell-based cancer vaccine for immunotherapy. Here, I'm bridging my research between Department of Medicine and Material Science and Engineering Department. For an extensive discussion on these research topics, please feel free to look up my other two talks as I directed in the box in this poster. As a faculty member, I plan to rationally design advanced biocompatible materials for precision imaging and therapy to enhance human health. For the beginning, I will be concentrating on addressing maternal fetal health. I'll be achieving this goal by means of designing new nanoparticles that ranges from hard to soft materials, hydrogels, and at the intersection of the soft and hard nanoparticles and materials which lies metal-organic frameworks. My materials design will lead to nanoscale probes, sensors, and deployable gels which can be tracked and visualized by advanced preclinical imaging modalities. Specifically, I'm excited about employing these tools in three research areas, which I'm going to delineate in the following slide. In my research program, I will be combining the expertise from materials design in my PhD and advanced biological characterization and cellular platforms, which I picked up on as a postdoc in the stem cell biology lab. With many nanoparticles in the pipeline nowadays, I have always wondered about the risk that these nanoparticles may impose on the fetus and how we lack any ethical and biologically relevant tools that this has led to the slowing of the translation of these nanoparticles to the bedside. Therefore, I'm planning to engineer cellular models that can recapitulate the maternal-fetal interface and can inform the nanoparticle community about the design parameter consideration for safe nanomedicine in the future. My approach will be to design self-organized 3D human pluripotent stem cells that are called embroid bodies, and later on I will move to organoids that mimic the physiological properties during development because these are made from the primary human cells themselves. From my postdoc, I know how to make the cell assemblies, which gives me a space for testing a wide range of nanoparticles with various physical-chemical properties that I'm going to rationally change. I will then apply multiomics analysis to elucidate the interaction of cells and nanoparticles. Yet one question will be how this small set of database generalize for unknown future nanoparticles. To answer this question, I will be utilizing machine learning tools to predict the mechanistic effect of a given nanoparticle, and then we'll be verifying our predicted results with mouse models. My second goal is to leverage my training in the area of developing cancer vaccine and antibiofilm agent for designing biomaterials that can detect, vaccinate, and treat the disease which leads to 8 million office visits per year. That is called urinary tract infection or UTI. This disease disproportionately affects women. I will hinge on my experience on the chemical cues which drives this disease, in particular the iron deficiency in bladder and proteases, which are enzymes expressed in an infectious environment. My nanoparticle and dynamically covalent cross-linked hydrogels, which I'm going to design as a media to deploy these therapeutics, will be trackable with advanced imaging techniques to reveal the molecular level, the location of the infection. One imaging modality that I'm really excited about is NIR2 imaging, which can map biological phenomena in the second biological window, where the body's own absorbance and scattering is minimum. I'm also excited to investigate the potential of my biomaterials technology in certain infectious diseases, such as COVID, where these nanoparticles can be repurposed for. I plan to engineer supramolecularly assembled nanoparticles combined with metal-organic frameworks to address a gynecological disease that is called endometriosis, which is basically the thickening of the uterus itself. It results in severe pain in women. I'll be curbing the immune microenvironment of the disease to reverse the scarring and fibrosis phenotype for healing pain and stopping their recurrence, which tends to happen quite frequently in this disease. Overall, I believe that with the help of materials engineering, machine learning, cellular models, stem cell biology, and multi-omics tool which I'm bringing under the umbrella of my program to your department, I can set the stage for transforming women's health, which can inform us on a larger scale about the human health in the long run. With this, I would like to thank you for visiting my poster today, and please feel free to contact me either through the chat or live Zoom session. Thank you.